I'm excited to introduce Tom Neumann. He's been a critical part of the ICESat-2 mission since the very beginning. He was served as the deputy project scientist during the development and implementation stages of the satellite in the decade preceding its launch. And he is currently the ICESat-2 project scientist. And he is very excited to be here today to give us an overview of the ICESat-2 mission. Take it away, Tom.
Thanks for the introduction. And all of that's true. I am excited to be here. I've certainly been working on ICESat-2 for a long time, but I wanted to say two things before I jump into slides. One is thanks to the organizers. This is the third time through it, and they've been able to leverage a lot of the work from the past hack weeks, both ICESat-2 and otherwise. But there's a ton of volunteer hours that go into this. I remember after the first one, I got with Anthony and Axel, and we're like, okay, is there a model here for actually supporting all of the work that goes into these, and would anyone be able to afford it? And the answer is kind of no. There's so much time that people have donated to this to make it a good experience. And both on the project side as well as the management folks above me, they see the value in these things. I forget how many ICESat-2 science team members started by doing one of these hack weeks to learn about it, talk to other people, you get ideas for a project. Next thing you know, you're writing a proposal and you're on the science team, and now you're paid to work with ICESat-2 data. So it's a super cool thing that Anthony and the team has put together. And the second thing I was going to say is that I learned probably as much or more than anybody from these, because while we were putting together ICESat-2, you have an idea of your requirements and here's your objectives and blah, blah, blah. But people are creative. And the kinds of questions that we get from these, it often opens up my mind to new possibilities like, oh, that's a better way of doing things. Or, ooh, if we put those two pieces together, that would really solve this or that or the other problem. So I'm really looking forward to hearing about all of the different projects going on. I don't know that I'll be a ton of help, but I certainly try. But you do have the experts here with you. So don't be shy. With that, share. And am I in full screen? I am. I got a nod from Jessica. That's great. Yep. Yeah. So as said, I'm Tom. I'm at NASA Goddard. But the whole reason I can make this presentation is due to the hard work of the entire ICESat-2 community, both science community as well as the engineering teams and that sort of thing. It really does take a village to do these projects. And I am privileged to be able to give this presentation. I often lead with this slide. It's a global mission, right? ICESat-2 is 500 kilometers up in space, and we're taking data globally. And for a while on Fridays, we would do these things called Photon Friday, or Fridays with a PH, because it's funny. It's also with a PH. And you can see all these cool examples from around the globe, various places, if you take a look at NASA ICE. ICESat-2 began with these 4 science objectives. This was big picture, what we were trying to do with ICESat-2. And I'm not going to read them. You can read them if you like, but there's 2 of them related to measuring ice sheets and changes in ice sheets to understand how they're impacting and interacting with the rest of the climate system. The third objective is about taking measurements to enable sea ice thickness. We're not able to measure thickness directly, but we understand that thickness is the really relevant scientific variable that many communities want. And then lastly, and certainly not leastly, is using ICESat-2 data to measure vegetation canopy height. The ecosystem science community is a really big community and has been using LiDAR for a long time. And we wanted to make sure our data was going to be useful for their science objectives as well. Uh-oh. Okay, here we go. So big picture, how this all works is here. This is a very technical diagram, but it has the 3 pieces that go into measuring the height of the Earth from space. There's 3 things you need to know. One is the range measurement. If I swizzle around my mouse, Jessica, can you see that? Yeah, you can. Yep. Cool. So yeah, that's just the range measurement. It's the distance from your instrument in space, in this case, to the Earth. And the way we do that is with green laser light, measure the time it takes to go all the way down to the Earth and all the way back again. That's one piece. The other piece is the next piece is the pointing angle. Which way is that laser beam pointed? You can imagine with my laser beam finger here, if I'm a little to the left, I'll get a different measurement than if I'm a little bit the other way. The third piece of the puzzle is, where are we in space? Are we over North Carolina or are we over northern Finland? So you want to be able to put those measurements of range and pointing angle in context. You can swizzle all those three things together in ground processing to turn that data into a latitude, a longitude, and a height at a particular time. And that's what ICESat-2 is all about. The instrument that ICESat-2 uses is called ATLAS, the Advanced Topographic Laser Altimeter System. On board up in space, it generates a single laser pulse in the green part of the spectrum, 532 nanometers, and it's split into 6 beams as it leaves the spacecraft. Those 6 beams generate 6 footprints, laser footprints on the ground, arranged in a rectangle pattern over here. That light reflects off the surface of the Earth, and individual photons are detected by ATLAS as they make their way back up to the spacecraft. So by having such a sensitive detection system, each outgoing laser pulse can be relatively low transmit energy, which is super cool. Lets you do a lot of interesting things. There are 6 beams. They are generated all simultaneously, and they're arranged in this rectangle pattern. And as the spacecraft orbits the Earth, these footprints make 6 ground tracks on the surface of the Earth. By slightly clocking or yawing the spacecraft, we arrange these beams into pairs so that you end up with 6 lines across the landscape, 2 of them almost directly underneath the spacecraft, a pair to the left, and then a pair to the right. And those pairs are spaced by just over 3 kilometers to the left and right. The laser on board ATLAS generates laser pulses 10,000 times a second. And at our altitude and velocity, that generates a footprint on the ground every 70 centimeters in the along track direction. Now, if it's clear sky, you actually get really dense data in that along track direction. If it's cloudy, maybe a little less so. You'll see lots of instances where you're interested in studying Arctic sea ice in summer. It turns out it's a really cloudy place. And so there'll be big data gaps where we just couldn't range down to the surface. The footprint size is another one that comes into play sometimes. They're small, 11 meters. And you can compare that with, maybe with the original ICESat, which was much larger as well as oblong. These are pretty circular as far as we can tell, and small, about 11 meters. I just have one slide on the transmitter and one slide on the receiver, just sort of big picture. How does the technology work? From left to right here, at least on my screen, we have 2 lasers on board, but only one of them operates at a time. Right now we're operating, let's say, this primary one. Goes through a couple of pieces of glass. Part of the laser pulse gets split off and sent to the start pulse detector, and that's the start time of when did this laser pulse begin. Bounces around off various things. It's split right here. The direct fractive optic element turns that single beam into 6. Actually, I should update that and make 6 little beams right there. And then the beam steering mechanism, little mirror that steers the beams wherever you want them to go. So to Earth, there's those 6 outgoing laser beams. I should have mentioned on the last slide, but I'll mention it here. You might notice that there are 3 relatively large arrows and 3 relatively small arrows. 3 of the beams are what we call the strong beams, and 3 are what we call the weak beams. And the reason we use strong versus weak is that the strong beams have about 4 times the energy as the weak beams do. You'll find, I think, that all 6 beams are useful for really bright reflective targets like fresh snow on sea ice or ice sheets. But over vegetated areas or darker surfaces, ocean water, pretty much the strong beams are where it's at. After bouncing off the Earth, you get these 6 streams of photons coming in to the ATLAS telescope. They get focused onto 6 optical fibers, 6 individual optical fibers, one for each. You go through some filters to get rid of sunlight as much as you can anyway. To the detection modules. The Atlas has two sets of detectors, but we're still using the primary set of detector modules. And there's a little switch here that lets you pick primary or redundant. And at that point, we're going to turn that green laser light into electrical pulses. So you're going to go from optical to electrical in this next slide. Each one of those detection elements, I apologize, it's sort of a busy figure, but bear with me. You've got these 6 spots over here on the left. Let's pick on one of the strong spots, maybe spot 1, because it's got a little circle around it. Light comes in, that optical fiber gets routed to the detector for spot 1. And the detection element we're using is what's called a photomultiplier tube, or a PMT. And that PMT has 16 individual detection elements in it. And what Atlas tries to do is spread that incoming light evenly across all of these 16 channels. And each photon gets routed to one of those 16. As that detection element, let's say it went to spot 7 here, that generates an arrival time for a particular photon. A returning strong laser shot over Antarctica often has something like 7 or 8 photons coming back in. So half of these would be illuminated and detecting photons. For the weak beams, there are only, we've grouped those elements together to make just 4 individual timing channels for each of the weak spots. The 4-to-1 ratio in transmit and receive transmit energy also holds up more or less for receive energy. And there are 4 times fewer pixels for weak spots than for strong spots. None of this usually matters because we take care of all of it at the lower processing levels. So you don't need to worry about whether a particular photon came in on channel 5 or channel 6. We normalize out all those differences and correct for any path length differences or electrical differences or what have you. So yeah, Atlas is always on. It's always detecting photons, and there's a few different things happening up in space. One is that the photon counting electronics, that is the little card that keeps track of all these electrical pulses coming in and which channel are they on and what was the arrival time, generates what we call an atmospheric histogram. So basically that's using 30 meters of height and just counting how many photons came in for this bin, this bin, this bin, or that bin, aggregating it over 400 shots. So that is what we call the atmospheric histogram. You'll note down here by the returns coming from the Earth's surface, you get bin counts that are relatively high. In this instance, it's maybe clear sky, so you're not getting a lot of reflections up from clouds up in the atmosphere. But it is pretty coarse, 30-meter bins. So you know where the surface is to within 30 meters, which would earn you a slow clap for most people studying ice sheet height change. It's pretty coarse. But it's great for clouds if you're a cloud scientist. Up on board, Atlas takes a look at the distribution of photons as they come back in and tries to figure out where the surface is. Atlas detects about 3 or 4 times more photon events than it can telemeter information for to the ground. So it has to do some skinnying down of what photon information actually gets sent. And it uses this intermediate step, what we call the altimetric histogram, to make histograms of returns as a function of height every 200 shots. And it uses those histograms to say, okay, the surface is probably right here. I'm going to set a telemetry band around the surface, and it's got a whole bunch of rules about how that works. But the upshot is these telemetry bands are typically between 50 meters and a kilometer, where it sends all the detailed photon information. So if you look at ATL03 over a relatively flat surface, like maybe the global oceans, you'll see a relatively narrow band of photons, maybe 50 meters high, 70 meters high. And over places on the Earth where significant topography, let's say the Alps, you'll have really wide telemetry bands with lots and lots of photons in them. If you plotted a long stretch of photon data, you'll see that band get wider and narrower as the topography changes. And those bands can change every 200 shots. So it's forever reevaluating how rough do we think the topography is and what photons should we send down. There's 2 slides in here on some of the more detailed numbers that I am not going to go through, but they're here if you'd like to read them later or you need to know. From there, gonna go on to this next one. Yeah, so Atlas is up there detecting photons, keeping track of transmit times, keeping track of receive times, keeping track of pointing angles, keeping track of where it is in space. And that data gets downlinked 7 times a day. We had been downlinking to 2 ground stations, one in Svalbard and one in Alaska, but the Alaska station went offline in September. So right now we're only going through Svalbard. And that data goes through NASA networks to NASA Goddard in Greenbelt, Maryland. The raw data is about 480 gigabits per day. And from there, it just gets bigger. Each of the data products have this ATL leading characters, ATL for Atlas. And then the number indicates the data product. Higher numbers are generally higher levels of processing. At ATL01, that raw data gets unpacked, converted from the binary, and turned for the first time into HDF5 format. ATL02 applies all those corrections for instrument effects that I mentioned. It takes times, temperatures, voltages, and calculates what the photon time of flight is, organizes the data by beam, and passes along the relevant spacecraft data that allows us to precisely determine pointing angle and position in space. So ATL02 isn't a super user-friendly product because you'd have to do what we call the geolocation yourself, and no one wants to do that. But as I mentioned, there's those 3 pieces: position of the observatory, pointing vectors for the beams, and then the photon time of flight. And in ground processing, we combine those to produce that latitude, longitude, and height at a particular time and put it into the ATL03 product. ATL03 has those heights for every individual photon. We geolocate as precisely as possible about 1 photon every 20 meters and geolocate the others with respect to that special photon. We call that special photon the reference photon. It turns out to be really computationally expensive to do a precise geolocation. And given our data volume, we can't, or we choose not to, geolocate every photon individually. So we have this 20 meter-ish length scale in there that's called we call it a lot of things, but a long track geolocation segment, or a geoseg if you're cool, or whatever. But there's 1 reference photon in each geoseg. All the other photons are geolocated relative to it. But the upshot is latitude, longitude, and height for every photon. And here's what some of that data looks like. The top plot is just every photon plotted, height on the y-axis, time in seconds along the x-axis. And you can see that this telemetry band is changing. It's relatively narrow, it gets relatively high. You can see that the rate of background photon noise is changing, relatively little over here on the left side, places where it's relatively higher. Most of those background photons are due to sunlight. The sun also puts out a lot of light in that part of the spectrum, the green part of the spectrum. We try to filter out as much as we can, but some of it's at exactly the same wavelength as our signal photons that we're interested in. One of the cool things O3 does is give you a first crack at classifying those photons. O3 is not telling you what the surface is, but it is telling you, hey, I think these photons are probably signal photons. So there's a parameter in there called signal conf pH, where we've used a histogram-based approach to try to figure out which photons are probably the same from the surface and which are not. And if you plot the low, medium, and high confidence signal photons for this stretch of data, you go from this, which is pretty noisy, but you can see the surface, to something like this, where it's done a pretty good job, but not a fabulous job, of pulling out the signal that's going to be of interest to most scientists. Lots of times we get asked about geophysical corrections, particularly for folks studying sea ice or oceanography. You want to know, what are these heights relative to, and what geophysical corrections have been applied. And here's a table of them. Ones indicated in an R are provided on ATL03 as a reference value. For example, the geoid. Geoid comes in handy for lots of things. There is a geoid value at the geoseg rate, at the 20 meter rate. on the ATL03 product, but it's just there as a reference. It's the EGM 2008 model. ATL03 doesn't do anything with it, but it's like, hey, it's here if you want it. It's available. Corrections with the C on it are actually applied as corrections. Things like the solid Earth pole tide, ocean pole tide, and so on are applied to those photon heights. And there is one that we considered applying, the change in the center of the Earth through time, or geocenter motion. And at least at this point, we're not calculating it, we're not applying it, we're not doing anything with it. So that gets a big fat no in the applied column. So maybe this would be a good time to mention that each one of these data products has a big document that goes with it called the Algorithm Theoretical Basis document. And that is all of the gory details about all of these things. They're all available online. Their acronym is the ATBDs. And if you looked at the one for ATL03, you'd see there's a section about each one of these, about what did we do with it? How did we choose that one? And how are we using it or not? Little flow chart for ATL03. I won't belabor it a ton, but you get time of flight, pointing, orbit determination, and you just start swizzling these things together. Coming out the other end is the data product. This is my favorite stretch of ICESat-2 data. It's the first stretch of data that was geolocated shortly after launch. I think it was October 2nd or 3rd of 2018. It's the middle of Antarctica somewhere. And it's an example of here's what the data look like. A little bit of background, but the surface jumps right out at your eye. The ATL03 product, as well as many others, are too big to simply have as a full orbit. So we break them up into regions. And each granule or single data file of ATL03 corresponds to one of these regions. We tried to be clever about choosing where those region boundaries are. For example, middle of Antarctica is region 11, but if you want the whole Antarctic ice sheet, you need regions 10, 11, and 12. I often refer back to this thing a lot when you're trying to figure out where you should be looking for data. I mentioned earlier a 500-kilometer altitude, and with our inclination, we collect data from 88 south all the way up to 88 north and everywhere in between. We have 15 orbits a day, and those orbits repeat every 91 days. That leads to 1,387 unique ground tracks around the Earth. You can download those ground tracks in KML version from our website. They are what we call RGTs, and if you're looking at a particular area, like today I'm in Fredericksburg, Virginia, there'll be a handful of RGTs that are always in the Fredericksburg, Virginia area, and it'd be a matter of sorting through and figuring out which ones are clear, which ones are cloudy, which ones are close to your area of interest or not. But yeah, typically you'll need a few pieces of information to uniquely identify ICESat-2 data. RGT is one of them, the date is another one, or what we call the cycle number, which 91-day cycle are we in. In the polar regions, we're trying to study elevation change. And to do that, we point at the same track over the Arctic Ocean or Antarctic Ocean or the ice sheets over and over again. So you really can compare the height from cycle 1 to cycle 2 to cycle 3 and so on. In the mid-latitudes, the goal is to enable mapping of vegetation canopy height to derive biomass. And so we developed a series of off points to densify the data through time. If these heavy blue lines were where data was collected during the first cycle, in the second cycle, we pointed off to the right to sort of split the difference between neighboring tracks. The next cycle, again, we're trying to split the difference again, and so on, so that through time, that coverage gets denser and denser. I'm gonna take a drink of water, pardon me. I think I mentioned all of the top part already. The only other thing I'll mention with this figure is that places where a reference ground track crosses another reference ground track are kind of special. Those crossover locations, you get an incredible density of data, or you can if it's clear sky. Each of Atlas's 6 beams cross 6 prior tracks from a preceding or a subsequent track. You have the reds and the blues. That generates 36 individual crossings. So that's 36 opportunities to look at elevation change between the pass 1 and pass 2, which can be really powerful. We use this daily actually to monitor changes in atlas range bias and whether it's able to measure the same height over and over again through time, data consistency. Our overall data product flowchart is here, and you're going to hear about these higher level products later. There's good reasons that they exist. One is that ATL03 doesn't tell you what the surface is. It tells you what's probably signal. And two, ATL03 is huge. I mean, it's gigantic. Hundreds of terabytes a year. And these higher level products aggregate that photon data. They find the surface. They apply other really smart corrections to give you the best possible estimate of the height of the ice, or the height or the freeboard of sea ice, or height of trees, and so on. We also are developing, and most of these are out by now, but the higher level products where you take all the ATL06s and you grid them into ATL14s and 15s. So that's a higher level product yet. The lower level products up to ATL03 were all developed by folks within the project, but we recognize that there are experts in satellite laser altimetry for many other disciplines out there. And so we worked with these experts to develop those higher level products, several of whom are on the call today, which is great. Make sure you use them if you have questions. I'll give a particular shout out here to Ben Smith at University of Washington with the ice sheet products, and Alec Petty. Alec Petty's not at JPL. Who made this slide? Alec Petty is at the University of Maryland, College Park. And I have no one to blame for that typo except myself, unfortunately. Usually if you're a good manager, you can find somebody else and I'll figure out how to do that. One question we're often asked are, how good are the data? How good are these individual heights? Kelly Brunt is our post-launch CalVal lead, and she developed and implemented the idea for this ground traverse in Antarctica along the 88 south line of latitude. In this little map here, you got the South Pole at the center of the figure, and she has led 3 traverses now that cover about 20% of that circle and survey the ice sheet height with GPS. And we then continually compare that GPS measured ice sheet height with what is seen from space. Here's a recent paper from Kelly using release 4 data. We're currently up to release 5, and she's revising these numbers, assessing ATL06. How good is the absolute accuracy and what is the precision of each of the 6 Atlas laser spots? And you can see the numbers in here, as well as the number of intersections. So at least over ice sheets, good to just a couple of centimeters, and typically somewhere 5 to 10 centimeters of spread around that mean value. So it's really pretty good data. Here's how they do it. This is a pretty cloudy day, not a great day for laser altimetry, but you got the tracked vehicle on the front, a long sled that's towing some camping tents for sleeping, and then you might be able to see this GPS antenna sitting back here at the end of the train, and that's the basis of measurement for that comparison. People have looked at ICESat-2 quality in lots of different ways, lots of different places, airborne surveys, that sort of thing. But generally, those are pretty good numbers. The middle of an ice sheet's like the best place you could do this comparison. So other locations are certainly worse. Urban areas, it's tough for ICESat-2. It's got an 11-meter footprint, and buildings are often smaller. One of the other key things to know is how good are those locations? You know, you get a latitude and a longitude and a height, but how well can you trust the locations? Lori Magruder at the University of Texas uses corner cube retroreflectors, tiny little piece of glass about as big as the tip of your pinky that are embedded in these, in this case, little plastic cap sitting on a bamboo pole. And that little piece of glass reflects green laser light really, really well. And these things show up in the data. And you can compare where ICESat-2 assigned the location of photons bouncing off of that little piece of glass with where those locations were surveyed to be. There are a number of these stakes down in Antarctica, as well as at White Sands Missile Range in New Mexico. If you're looking at the photon cloud in, I think this one's in White Sands, you can see these little red returns up here that are just above the overlying surface, and you can use those to assess the geolocation quality. as well as the footprint size of the ICESat-2 footprint. But those locations in release 5 data, which is what you'll all be working with, are good to about 3 meters. In some cases, a little better, some cases a little worse. It's a staggering achievement to me that each individual photon, its location is good to about 3 meters, measured from 500 kilometers away from a spacecraft moving 7 kilometers per second. And yet they can figure out where on the surface of the Earth that photon bounced off of to within just 3 meters. Really impressive. Of course, our data products go out to the public as soon as we can. They're served through the National Snow and Ice Data Center, and I've no doubt you'll hear lots about that in the coming sessions. So far, we've over 4,000 users, 4,400 and change unique data users to date. And NSIDC has served up over 22 million files from May 2019 through February 1st of this year. The number of users for each product are on this next slide, if it's going to render here in a minute. Thinking about it, there we go. The winning product, that is to say the best product, is clearly ATL-03, the product which I personally was involved with, 1,970 users. ATL-08 is a far and distant second place with 1950. That's led by Amy Neumann at the University of Texas, and we have a sporting back and forth every month when this report comes out. Occasionally, ATL-08 pulls into the lead. I simply offer a $20 bonus for every new ATL-03 user, and we just move right back into the front, which is great. Some of the newer products they have not yet developed their user base, and I expect some of these are going to be useful for y'all this week. So we'll see some of those numbers start to tick up. After 3 years and change, Atlas is doing great. We have had a couple of hiccups on board, anomalies, but nothing we couldn't recover from. There are some small data gaps from that. Over those first 3 years, the return strength, the number of photons per shot that's coming back, has dropped by about 10% over 3 years. But fortunately, the transmit energy from the Atlas lasers can be adjusted. We're currently running at energy level 4 out of a possible 11. These lasers actually do go up to 11. And sometime this year, we'll bump up that transmit energy to get it back to where we chose to be, where we initially were. The other one we're often asked about is fuel. So far, best estimate, we have fuel into the early 2030s. So it's worth it to spend the time, in my opinion, to get to know and how to use ICESat-2 data, because we already have 3 years of data, and knock on wood, we'll be getting another 9 years worth of data if all continues to go well. Early on, there were a number of groups that were kind of reluctant to dive in because they're like, well, let's see how well this thing lasts and what the data quality looks like. But data quality is great. Spacecraft is healthy and all is well. This is my closing slide. We've had over 1 trillion laser shots that collectively returned 12 trillion individual photons, which is a shockingly large number, but all is well. We're up to release 5. You got the dates right there. Thanks for your time. I'm happy to take any questions.